Good morning, everybody. Today we have Codeforces round 816. It's a Div 2 round with kind of a funny announcement, but we'll jump into it here. We are going to start officially exactly 10 minutes late, so I'm going to wait 20 seconds here. The announcement was kind of funny. Large text to get your attention, so hopefully there's some sort of reference to that in the problem statement, but we'll see. Yeah. I guess I woke up a little late. Like 7 or so. Alright, here we go. Let's jump into problem A. Cross market. Stanley and Megan decided to shop at the cross market grocery store, which can be represented by a matrix. Stanley and Megan can move to an adjacent cell using 1 unit of power. To speed up the shopping process, Megan brought her portals with her, and she leaves 1 in each cell she visits. If a person is in a cell with a portal, that person can use 1 unit of power to teleport to any other cell with a portal, including Megan's starting cell. They decided to split up. Stanley will go from the upper left cell to the lower right cell, while Megan needs to go from the lower left cell to the upper right cell. What's the minimum total energy needed for both of them to do that? What's the cost of using your portal? 1 unit of power. So the height plus 1, unless the height is 1. Okay, so yeah, if the height is 1, then it's just 2 times the width. No, it's not. It's cheaper. Okay. So we need to do some kind of annoying stuff here. N is the height. Looks like it. So I think n equals this, m equals this. So if n equals 1, then dot point line m plus 1. One person moves all the way across. I guess it's m minus 1, because you take that many steps, and then 1 more for the other one. Okay. Otherwise, I suppose you can skip either one of the dimensions, huh? You can either skip up or skip right. So, in general, I guess this is out.println math.min of n m plus n plus m, or n minus 1. We'll just say this, n minus minus m minus minus. So the min plus 1 person goes all the way, plus 1. Yeah. Did I not print anything? Fifteen, 15, 1. If it's 1, 1. Yeah, okay. Submit A. JavaScript. Java. Let's move on to B, beautiful array. Stanley defines the beauty of an array, which contains non-negative integers, as follows. The sum of this over k. Is k a constant? Stanley told Sam the integer k and asked him to find an array of non-negative values such that the beauty is equal to b and the sum is equal to s. So you round down each thing and sum them. Okay. All right, so you have this, and then you have the number of elements, k, beauty, and sum. So the beauty, what is the beauty? Yeah, it might not exist. Yeah, the beauty is just the normal sum. So you can have just like a bunch of elements that are 0 and then one that's bigger. Right? For the beauty anyway. Or for the beauty. The beauty is just everything's times 0 except for one thing. And the sum is just the value under mod. Okay. Cool. So the first one is n. Divide by beauty sum. All right, and then we'll have long array. Oh wait, what is, so this can be up to this. Okay, so this is beauty array equals new long array n. Long array original is new long array n. Okay, and then yeah, I guess we want to check to see if it works. So beauty array 0 equals beauty. Sum, okay. So then sum minus equals beauty times divide by. This will just be original at 0 plus equals beauty times divide by. Okay, and now we need to distribute the rest of sum of everything else. So for n equals 0, less than n plus plus, original at I plus equals math.min of sum. Well, okay, what if sum is less than 0? Otherwise, the min of sum and divide by -1. Because we can't increase the beauty L here. And then we should be good, right? So now we're done. And sum minus equals that. So if sum is not equal to 0, then out dot print line -1. Otherwise, out dot print line. Oh, we can't do this. I think we're good. Let's try it. Yeah, next long. Thank you for putting that in samples. I think this should be equivalent. Okay. What about this? So okay, looks good. Let's move on to problem C. monoblock. Stanley has decided to buy a new desktop PC from the company Monoblock and needs to solve the CAPTCHA on their website. The awesomeness of an array is the number of blocks of consecutive identical numbers in which the array can be split. For example, the awesomeness of this array is 1. Is the number of consecutive identical numbers. So like you compress it, how long is it? This many, 3, okay. You're given an array n, there are m queries of 2 integers. A query means from now on the ith element of the array is equal to x. After each query, print the sum of awesomeness values among all subsegments of the array. Okay. Alright, I see. So, yeah, that part's kind of weird, but I think it's fine. So, yeah, let's think about this. So initially you've got all of these elements, but importantly you have all of these spaces. And the spaces are what matters. So the question is how many times, so everything will be at least 1, but if it crosses a space that's flipped, right, you've got like some of these flipping spaces. Maybe each of these spaces, it changes here, it changes here. Every time you cross a space, that is how it works, right? Yeah, it would be nice if they gave an example that's like not I think what happens is if you have something that's like 2, 2, 3, 2, 2, this is 3 blocks. I think it's like this. But it would be nice if they had that in the samples or like explained it somehow. Anyway, I think, yeah, so if you cross this, it's 2, and if you cross this, it's 2, and if you cross this, it's 3. So we need to like count this. So we need to know how many subsegments are each of these part of. So this is part of 1 times 1, 2, 3, 4, 5, so 5. This is part of 2 times 4, 8. This is part of 3 times 3, 9, 8, 5. And then you just need to maintain these. Pretty easy. What is n and m? N is the length, m is the number of queries. Okay. So we'll go through each query and then solve it. So then how do we solve a query? Well, we need to be like, what's the multiple of each thing, first of all? Boolean array is flip equals new Boolean array n. So let's flip it I equals 8i is not equal to 8i plus 1. Alright, so we have all of these, and then we also need int array, or I guess long array, value of, just new long array minus 1. Value of at I equals I plus 1 times the other side, which would be, I guess, n minus 1 minus I. Alright, so then long ants be 0, and for int I equals 0, plus 1 plus plus. Ants plus equals value of at I times is flip. If it is, then we count this once, otherwise we count it 0 times. Is flip at I, I mean. Okay. Now we have this. All right, so what does this query say? We do this after each query. Okay, so int index will be this, set 2 is this. All right, so we'll say ants minus equals, so if index equal to 0, it's annoying. Else if index is not equal to 0, I guess we'll say ants minus equals value of at index times is flip at index. If it is 0 or 1, otherwise 0. Let's just make a value method. And this is index minus 1. Index is not equal to n minus 1, then ants minus equals this, but this will be index. And then we'll add these back at the end. All right, so then we'll say a at index equals set 2. And then flip at index minus 1. So if index is not equal to 0, flip at index minus 1 equals a at index minus 1 is not equal to a index. Let's flip. And then we need, if this is not equal to n minus 1, flip at index will be a at index not equal to a at index plus 1. And then I think we should be good. And then out.println the answer. Not quite. All right, so plus 1, right? Is it ants plus 1? So 4 plus 3 plus 2 plus 1. What is 4 plus 3 plus 2 plus 1? 10, right? So am I off by 1 here? This is annoying. what is the answer initially? 20. Okay, so four. Well, yeah, so what is this? So it's like, it's going to be 10 plus 1, 2, 3, 4. This is 10 plus, oh, it's, yeah, 1, 3, 4 plus 1 plus 2 plus 3 plus 6 plus 1 plus 2 plus 3 plus 1. So this is this is 20. Yeah, 20 is right, isn't it? Okay. Yeah, that's right. Ah, set 2. This one. Wait, am I wrong? I have to go to the bathroom. So this is 4, 6, and 4. One, 1, 2, 3. What the heck? One. So how many times? Yeah, this gets split in 4 ranges. 1, 2, 3, 4. This gets split in 6. This gets split in 4. And then 2. And we have 5, 4, 3, 2, 1. Or no, sorry. 1. Oh yeah, 5, 4, 3, 2, 1. So I'm off by 5. Okay, that's it. Okay. Dang it, that's annoying. Way too long. The narrator has an integer array A with length n, but will only tell you the size n and q statements, each of them being 3 integers, I, j, x, which means that AI is equal, or AI or AJ equals x. So he gives me a bunch of pairs, and he says neither of these have these bits. Okay. Find the lexicographically smallest array that satisfies all of the statements. So each bit is independent, right? Yeah, each bit is independent. And then we're saying, how are my friends doing? It does seem quite easy. Why are people not getting it? Anyway. each bit is independent, and people are saying for this bit, neither of these have it. For this one, at least one has it. Seems easy enough. And M, what are these? The edges? I, J, X? Okay. Okay, so what do we need? I guess we can just build the array ourselves. Int from to, and then val public edge. Int from int to int val. Okay, so we build this, and then we'll get these, and we'll say graph, edge e equals new edge from to val, graph from add e, graph it to add e. And then this is probably easier to not do it like this. Okay. Yes, we've got this. Can I and J be the same? They can be, that's annoying. Alright, yeah, we can handle it, it's just bothersome. Okay, so sometimes things are forced to be on, sometimes they're forced to be off. It might be impossible, right? Well, it could be impossible, but I guess they won't give us a case where it's impossible. This bigger than, no, 2 to the 30. Yeah, okay. All right, so then this isn't an int, it's an array list edge array. And then what else do we have? We probably also need the answers, right? All right, and then here we just print it. All right, so now we need to solve each bit. So how do we do this? Boolean array is 1 equals new Boolean array. N Boolean array forced 0 equals new Boolean array n. I guess we also need forced 1, huh? Okay, so okay. So if e.value does not have this bit, then this is forced 0. If we have any edges that don't have this bit, we have to be a 0. Okay, if e.I equals, or if e.2 equals I, then forced 1 that I equals true. All right, cool. So now we have voice correct. Now we have this, and then at the end we'll just say for int I equals 0 less than n I plus plus if is 1 at I. If this is a 1, then what? Then we set it to a 1. Then answer at I plus equals 1 left shift bit. Okay. So if forced 1 at I is 1 at I equals true. And then continue. If forced 0 at I then is 1 at I equals false. Okay. What else? So now we need to see, can we make this a 0? All right. So for edge E in graph at I, if e.2 is less than I, and e.2, well, everything before us will tell us whether we're, I guess we can just not do that. So yeah, let's see. If, okay, this better be a 1. So if e.2 is less than I, and not is 1 at e.2, that means that we need to be a 1. Then is 1 at I equals true. Otherwise, if forced 0 at e dot 2, then is 1 at I equals true. I think we're good. Pretty dang easy. I guess it is easy. I just didn't see. Maybe people are just slow today. That's fine. I woke up late too, so can't blame them. Long way home. You live in a country that consists of n cities. There are bidirectional roads between some of the cities, and you know how long it takes to ride through each of them. Additionally, there is a flight between each pair of cities, and the flight between these two cities takes the square time. Okay, hold on. So we have a bidirectional road. Okay, also there's a flight. Okay, and the flight takes this. But there are also some roads, so you might not want to take the road, or you might not want to take flights. Okay. Stanley is quite afraid of flying because, wait, the flight between each pair in some of the cities. Okay. He's quite afraid of flying because of watching something, and he can take at most K flights. He wants to know the minimum time of a journey to each of the n cities. Oh, the difference squared. Oh, I see. All right. Let's do the minimum time of a journey to each of the n cities from city 1. Ah, K is small. Okay, cool. Yeah. I think I can do an n log squared. Some segment tree stuff. Oh, maybe not. Maybe that's actually really hard. Yeah, so you've got, this is kind of weird, but you've got like, it's the distance squared too, not just the distance. Oh, and the number of flights. Surely there are some observations here that I'm missing. So if your shortest path would be something like this, you would only take flights that are like here, here, here. You never take a flight. Like, it makes no sense to take one of these flights. Because instead of taking the flight, you could just go like that. A shorter flight, and you save more. You want to start at city 1? Okay. So what if 20 times we say 20 times you can either fly from anywhere, or you can do disjoint set, right? Or you can do, sorry, dexterous. Alright, so how do you do this? Like, this is easy. So fly from anywhere. So you want to know, you have like a bunch of heights. Then you want to know for this one, what is the smallest parabola? Oh, they don't look like that. They look like this sort of thing. You can do this with convex hulls. You can do one of these things. It's a bit annoying, but it's doable. You can do so we want so every space has a cost, ci. So you want the min of, and then we want to travel to j by flight. So you want the min of ci plus I minus j squared. So this is equal to the min of this plus I squared plus j squared minus 2I times j. So this j squared part is u, so we can take that out. This is a constant. Yeah. Man, so it looks like this is just, yeah, this is a constant. And then this is your factor. This is your slope. Okay. Yeah. So this is n log n, I think, or this is n times 20. No, it's n log n, because we do the dexters each step. Okay. I think this is math. Maybe it's DP. Or utilities? No. It's kind of like a linear. I guess I don't really want the linear one. No, I don't want that convexel. I sold DP. Okay. Pretty clean. Okay, so yeah, what do we need here? We need to do this. Okay, so we have the number of cities, the number of roads, and the max number of flights. Okay. Int n cities equals this, and roads equals this, and flights equals this. And then we'll have an array list edge, array graph, array list edge, and cities. Okay, and then for int I equals 0 less than n roads. And from equals this, minus 1, 2 equals this, cost equals this, and graph from dot add new edge from to cost. What's wrong with this? Okay. Oh, did I paste again? Okay. Add this and then add 2 to from cost. Okay, so we've got a graph. We need long array, distance 2 equals new long array, n. Dot fill, distance 2 along dot max value over 2. Distance to at 0 equals 0. Alright, so now we need static void extras. We'll have a long array, o distance 2. I guess we should return a long array, probably. Yeah, it's just multi-source Dijkstra's. And then we need a graph. And probably also an n would be useful. All right, so yeah, so we need a state. So int node long cost. Okay, so we need a priority queue of state. So we'll add a new state. This will be node I with distance 2 at I. Okay. Or I guess, yeah, we'll just make this distance 2. So then we have this. We just say, well, sure. States dot is empty. State next equals states dot remove. Then we need to consider all of these edges. So if distance 2 at next dot node is not equal to next dot cost, then continue. This is expired. Otherwise, for edge E in graph at next dot node, long new distance will be next dot cost plus E dot cost. And then, yes, we have this new distance. If distance 2 at E dot 2 is greater than new distance, and then we also want to add this state. Okay, so keep doing this until we run out of stuff, and then we're done. Okay. So then we'll do Dijkstra's distance 2, the graph, how many flights? N flights. No, this is just n. Alright, and then for i equals 0, that is less than n flights, plus plus. We'll do something, and then we'll do Dijkstra's. This would be static void convex hull. Long array, distance 2 into n. hull distance 2 Dijkstra's, and then we need to print the answer. So this will be out.print line distance 2 at I plus a space, and then, or out.print. Multi-test case, single test case. All right. So that should be fine. We probably want this part better, or we need this part better, but I think that's it. Yeah, okay, so how do we do this convex hull part? So we have distances to everything. We need to take the flights that are useful. Yeah, we get one flight from each thing. Okay. So the flights can go in either direction. This will be convex hull, go right, distance to this one, long array reverse equals okay, and then for equals 0 less than n equals plus, we'll say distance 2 at I equals map.min, distance 2 at I, or yeah, okay, or map.min of after going right at I, or rev at n minus 1 minus I. You could also go left. Okay. Cool, so we've got convex hull. Now we just need convex hull go right, and I think we're done. Okay. All right, so what is this part? We don't need any of this. So we need the math. Okay. Every space has some cost. Can you get rid of this underline? I don't like it. Thank you. Every space has some cost. And we want to travel to J. Yeah. So we have this. This is just distance 2. So is this min or max? We want min, right? So -1. Okay. Then, yeah, I do this. This is really 2. So we're going 2 each thing. So if 2 is equal to 0, then min cost to fly 2 at 2 equals line.max value over 2. Okay, otherwise, we can actually fly there. So otherwise, min cost to fly 2 at 2 equals dp dot query 2 plus j squared, right? Plus 2 times 2. So this is all factored in, yeah. So plus this, yeah. Okay. I suppose this is true in either direction, so maybe we could combine these into one. Let's just do that later, only if we need to. Okay. I don't like these problems. Okay, so then, yeah, now we need to like add my line. dp.add, yeah, I'm in B. So along B will be distance 2 at 2 plus I times I, plus 2 times 2. Along M will be minus 2 times I times 2. M and B. Okay. Then for n equals 0, let's do n plus plus. Distance 2 at I equals math.min. And distance 2 at I, or min cost to fly I. And we're done. What are the odds this works? As expected. Whoa, whoa! Dude, so cool. Does this work? 0, 1. Yo! I got so close! Is this right? Whoa, dude. That is, oh, for real? Come on. Come on. Come on. Alright. Alright. What's TLEing this time? Yeah, I can do the convex hull linear actually, probably. Cause I can add them all and then query them all. Okay. Yeah. So we can speed this part up a bit. This doesn't. Yeah, if you square it, it doesn't matter. Right? I minus j squared is equal to j minus I squared. I think it should be. Yeah, because it's negative and the negative one disappears. Okay, yeah, so this can get deleted. So we can have like a go both. That's just what this is. Okay. Let's get rid of this here. This is a factor of 2. Well, it's like a factor of, I don't know what it is. It's somewhat faster. Alright, so we got this, and then we don't need this part. Okay. So maybe we will add all of this first, and then query it all later. For n equals 0, as less than n is plus, and we'll query. So this is add this is the query part. And we don't even need this. We can get rid of this. Yeah, does this still work is the question. So we need problem E. Surprisingly, it might. 146 0 1 1 2 3 3. Okay, so this is a decent amount faster. And then I think we can get even faster with convex hull linear if we need it. I think we can remove like a log factor from the non-Dijkstra part. Can we ever get rid of the Dijkstra part? I don't think so. Looks like a TLE still. Okay. Should be able to get this. TLE again. Okay. Well, I guess I should double check my Dijkstras. It's easy to write an n squared Dijkstras by accident. Yeah, they're only 10 to the 5th things, right? It's only 10 to the 5th of them. Yeah, only 10 to the 5th. So, I don't know, it feels like it shouldn't be that bad. So we add each of these states. We call this 21 times. 1 per pilot. And states is not empty. Get the next state. The distance to it is not right, continue. think this is legit. Okay. So this is just too slow. What's the slow part? Add and query. Add new line. I guess this is kind of a lot. Okay, so where's my convex hull linear? Yeah, that's fine. That's what we're doing. Max number of lines. Okay, are they added an increasing slope or decreasing slope? Convex hull linear, I call this. Okay. How many lines? N lines. They added an increasing or decreasing slope. Okay, so the slope is decreasing, right? Negative, and this increases. Oops. So the slope is decreasing. So -1. All right. C is -1 if they are queried from large x to small x. 0 if no particular order. 1 from small x to large x. So they're queried from small to large, right? Queried from small to large, -1. And then these are min, so we want false. Does it just work? So just a copy paste? Dang. What am I doing wrong? Oh wait, it's 1. Okay. Why was it extended 15 minutes? Wonder why. Oh, we got it. Look at that. Nice! Okay, well that gives us just enough time to solve F, I guess. These TLE, RTE. Alright, let's solve F. Crop squares. This is an interactive problem. Oh boy. Farmer Stanley grows corn on a rectangular field of size n by m, with corners at points these. The year of harvest was plentiful, covered the whole corn field. The night before the harvest, aliens arrived and poisoned the corn in a single square. The corn in the square must not be eaten, but you can not distinguish it from ordinary corn by sight. Stanley can only collect a sample of corn from an arbitrary polygon and bring it to the laboratory, where it will be analyzed, and Stanley will be told the amount of corn in the sample that was poisoned. Soon, the harvest will soon deteriorate, so such a study can be carried out no more than 5 times. More formally, it's allowed to make no more than 5 queries. Each of them calculate the intersection of area between a chosen polygon and the square of poisoned corn. It's necessary to find out the coordinates of a lower left corner of the drawn square. We got 1,000 intersection points. Well, it seems pretty easy, right? Just do a saw. Do a sawtooth in both directions. Yeah, why is this hard? I don't see why it's hard. I don't see it. Can I get a new one, please? Don't save. Alright, so you've got a big box. Apologies for my horrendous drawings. Maybe we do this. Boom, big box. And then inside of it, you've got big box, please, thank you. And then you've got like a little square here. And why don't we do one of these things? Right, so this is okay, I guess that's not true. But if you go like this, maybe it's true, it's unclear. So if this distance here is the length of the square, it's going to be height 1. So all that matters is like the amount of area will give you the x-coordinate. So we can do it in 2 queries. Can we do real number queries here? Or these have to be ints? 2 real numbers. No, it's 15 digits. Polygon of strictly positive area, no self-intersections. Yeah, so we can do it with way fewer bounds, I think, right? So they give us a thing. We just want the, yeah, this is easy. It's easy. Okay. Right? I think this is easy. I don't know, we'll see. Okay, so this is problem F. Scanner FS, new scanner system.in. Okay. Then what is this? N and M? And then equals this. And then equals this. They give us this field size, but it doesn't matter, right? We'll just do it 100 by 100. Static class rec double x y. Yeah, I think this all just is fine. Okay. Array list vec to print this new array list. So how do we do this? We'll start maybe we, yeah, let's do one of these. So here's the box. This is 100 by 100. So we're gonna go here. Oh, yeah. What do we want this to look like? Probably here. So we'll start it this, and then take this one down. And then this is this, so we need this to be 1 away, exactly 1 away. So this is at every integer, so it'll hit here. Okay. Okay, so to print dot add new vec. So this would be x minus 1, y minus 0.5. And then add new vec. This would be 100, or sorry, minus 1. This will be y 100.5. And then we probably also want to add the start. Yeah. So then this will be, the x will be 100, and the y will be 100. Okay. Then for int I equals 100, or do you want to start at 99? I guess start at 99. Greater than or equal to 0, I minus minus. Wait, does the are we allowed to query outside of the field? I guess I'll ask. Is it okay if our queries include land outside the field so long as all will be or have been? Okay. Yeah, I'm not too worried about this. It should be pretty easy, I think. At least in 30 minutes. Yes, okay. Yeah, this should be very easy then. Then this approach works. Okay, so then we need to add x0, y will be I plus 0.5. And then add the same thing 1 unit below. So this will be, nope. And then add 100. So we go, we end in 0.5, then we end in 0, 100, 0. And we go to -1, 0.5. Ooh, we don't want that, do we? Well, it doesn't matter. Yeah, it's fine. Okay, cool. So we have this, and now let's print it. Static void print. Print, and then we also probably want print rotated, right? This will be an array list of vec points. This will be an array list of vec points as well. So for vec v in points, we'll say this out v.x space plus v.y. You start with a question mark. This out question mark plus points dot size. Print all the points. Does that have to be in clockwise or counterclockwise order? Okay. Okay. This will be print the y and the x. So flip it. Yeah, okay. So print this. Double ans1 equals this. We need print to print r to print the ans2. So yeah, so double. So this is just like the %x, right? If it's 100, the middle is at 100. Yes, this is just %x. It's just %y. All right, so then double TLX will be %x times 100. Scale it up. Minus 0.5. And then BLY be this times 100 %y times 100 minus 0.5. And then we print the answer. Okay. Sure. It's kind of hard to test, but let me try. Let's say it's 1 by 1. Okay, so I don't know. Should we submit it? At 0, 2. The area of intersection of a chosen polygon What the heck? Wrong output format. X coordinate is out of range. What was the... Okay. Sure. So let's just say this was 0.5. What do I print? That's pretty close to right, though, is the thing. Oh, ooh, this is not right. Yeah, this is not right. This is 100 minus this. And this is also 100 minus it. Okay. So let's say it's 10 by 10. 0.1, 0.1. Yeah, I think that's right. Dang, wrong answer for just 5. Did I get the first ones right? Okay, so there's a single. Okay, so what do we do? So we can say, oh wait. Did I not have BLX here? I must have. Height, width, right? So n is the width. Okay, so it's width, height, right? Yeah, width, height. Okay, and then here we need BLX equals math.min, BLX or width minus 1, BLX equals math.max, BLX or 0. BLY, it's height. Okay. It's at most 100 by 100, right? Single test case, yeah. This should be cyclic, right? 8, 100, 7.50, 7. Yeah. Has side length 1. I pick a 1 by 1 square. 1 by 1 square. Well, so clearly my queries are okay, right? If they pass samples, they're definitely okay. Just like not accurate enough? How could this be wrong? Maybe a long double issue? But why is this a problem? Seems really, really right, though. I don't see why it's wrong. What? Okay. Fine. Interesting. I don't really like it, but okay. Yeah. That's kind of BS. This was right. These are right. I just don't like my print format. Oh, man. What was wrong with my print format? I want to see now. I want to see what test case I got wrong. That is hard to, like, watch out for, though. Like, it's... I'm not totally blaming, like, the authors, because that's, like, an easy thing to miss. Okay, we now go with solutions here. We have 15 minutes left. We'll go through them real quick. Alright, problem A. So, yeah, in this problem, you've got one person who starts on the bottom left, wants to go to the top right. One person who starts on the top left, wants to go to the bottom right. And the person who's going from bottom left to top right, the red person here, they will leave teleporters at every space they visit, and the blue person can travel from any teleporter to any other teleporter. So in this case, you can go something like this, the red person goes like this, and then the blue person teleports all the way down. But also, if you wanted, the red person could walk up a bunch, and then across, and then up, and the blue person could teleport across. So the blue person in one step can skip either all of the X's or all of the Y's, depending on the path. And you want the minimum number of total steps taken, right? So this teleport counts as one step, but in total, blue takes 1, 2, 3, 4, 5 steps to get to the bottom right. And red takes like 5 or 4 steps across the X's and then 6 steps across the Y's. So red takes 10 steps, blue takes 5, in total that's 15. And that's the minimum possible way of doing it. So you want to know what that is. And the key observation here is that this teleport can save you, like, what red is going to have to take the width -1 plus height -1 steps. Blue will have to walk across one dimension, but the other dimension, he can skip red's steps. Right? He can skip the other dimension with just one step, just the one teleport. So yeah, the answer is like, you have to pay for one of them. Yeah, you have to pay for, okay, so, if it's a 1 by 1 square, then the answer is just 0. Otherwise, you have to pay for, like, you have to walk across almost all of them by one person. Or one person has to walk across all of them minus the last, these 2 steps. Because you start on the first square, not the 0th square, right? So you have to walk through all of them, and the other person has to walk through all of one dimension, and then a teleport. That's your answer. Obviously, you don't teleport if it's 0 by 0, so that's why you get it for free. Okay. Yeah, that's the solution to problem A. A little annoying, but it works. Okay. For problem B, this is kind of like a very useful problem for understanding like how division works. The important part here is like rounding down. Like you have to know what rounding down means. So you have one array, and you're making another array by rounding down each element after you divide it by k. So you'll know what k is. You're going to take your first array, divide everything by k, and then you get the second array, and you chop off the remainder. Now you want to make a new array, or you want to make an original array, so that the original array has some sum of s, and when you make this new array by dividing everything down and then chopping off the remainder, you want the sum of the new array to be b. Right? You want to know, first of all, is it possible? And second, find some way of doing it. Now, the way this works is like the sum in the second array is going to correspond to a certain sum in the first array. So if the sum of your second array is 5 and k is 10, those 5 things each correspond to a sum of 50 in the first array. But everything, even like those 5 things and also other things which might be zeros, everything can have up to, if k was 10, can have up to 9 elements, or 9, up to like 9 that get rounded down, right? 9 divided by 10 is 0, remainder 9. So you can remove the 9 from that thing, which might be a 0 at the second array. So the amount that you remove is like, that corresponds to, maybe this is just obvious and I should be explaining it, but the amount you remove corresponds to what k is, and that's your flexibility in the sum. And then the amount that you divide by, that's going to be b. So it's just the 2 different parts. So we can actually simulate it and see like what it looks like if you do it. I just put all of my value in the first element of the beautiful array. So I just put them all there because it doesn't really matter which element they go to. I put them all in the first element. And then that's what the original element will be. And then for the sum, I distribute the sum as needed to all of the other spaces. So yeah, so like, let's do an example here. Let's say, yes, we can do this first, or let's do an example that's possible. An example here, 38. Okay, so we have 5 elements. We're dividing by 4, and we want to have 7. So I'll say this is 7, and then the rest are 0. 5. Okay, so this is the array we're going for right here, and we want the sum to be 38. Well, 7 times 4 is 28. So initially we have 28, 0, 0, 0, 0. So this is our array. But we need the sum to be 38. And we can add up to 3 on each thing. So we'll add 3 here. So we'll say plus 3, plus 3, plus 3, plus 3, and then, or plus 1, I guess, right? So it'll be, these add up to 10. And we need 38 as our sum. And importantly, each of these are divisible by 4. So if we do each of these divided by 4, we'll get something remainder 0. So we can have up to something remainder 3, and we won't change this beautiful array. Beautiful because it's how the problem defined it, I guess. So yeah, if we do this, then we get 31, 3, 3, and 1. And if we divide and floor everything, we get the same array on the bottom. And that's what it looks like. So we can run this real quick. Yeah, there we go. That's what we got. So yeah, here's the code for that. It's not too exciting. You can go through it if you'd like. Yeah, that's problem B. Let's talk about problem C here, monoblock. So in this problem, you have this like long array of numbers, and every time the number changes, so in this case it changes from like a 5 to a 7, you cut the array at that point. In this case, it changes from a 1 to a 7 here, so you cut it here. Changes from a 7 to a 9 here, you cut it here. In total, this is like 3 blocks. So what you need to answer is, you're going to do a bunch of update queries, and after each query, you want to know the answer to the question. And the question is, if you look at all continuous ranges in the array, and you split each of those up into blocks, how many blocks do you have total? So, like, this is your array, 1, 2, 3, 4, 5, right? You're going to look at just 1, just 2, just 3, just 4, just 5. Also 1 and 2, 2 and 3, 3 and 4, 4 and 5. Also 1, 2, 3, 2, 3, 4, 3, 4, 5, and so on. You're going to look at all of these things, all of these arrays. Then for each array, you want to know, if you do this splitting thing, how many groups do you get? And then you add those all up. So an important thing to consider here is what defines like an increase in a block. And that's like this split instance. So if we have an array that's like 1, 2, 2, 4, 5, if the range we're interested in crosses this, then it will have one more split point. Everything's going to have one block initially, because there's something in the array. But then when it changes, we're interested in that change. And these changes happen between elements. So it happens here, it happens here, it happens here. So really what we want to know is, well, we know how many ranges there are going to be. It's going to be like n choose 2. But what we really want to know is how many split points are included in all of these range sums. So an easier way to thinking about that is, well, let's consider a particular range sum, or a particular spot here. How many times is this spot included in some range? Because not all spots are included the same number of times. The spots, like this spot here, it's only included in ranges where the left endpoint is this 1. There are only 4 of those. But this spot here, if the left endpoint is one of these 2, and the right endpoint is one of these 3, it'll include this spot. Now this isn't a split point, so it doesn't matter. But if it was, like in this case, the number of times this is included is 3 times 2, right? For each of these left endpoints, we have 2 right endpoints. So this is included 6 times in total. So the number of, other than the base number of things, the number of additional splits that happens in this array is 4 for this. This is included 4 times, right? And this is a split. So this change happens anytime you have this left endpoint and one of these right endpoints. This is 4, this is 6, and this is 4. So in total, this is, what, 14? But also, we have 5 times 6 over 2. So that's 15. We have 15 different ranges in total that we pick here. And for each of those start with a block. So the answer here is going to be 14 plus 15. 15 because there are 15 ranges in total, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So the answer is 14 plus 15, which is 29. That's where it comes from. So yeah, I kind of went over the important parts here, but basically what we need to maintain is like where all the split points are, and also the number of times each particular element is important. Or like how important each element is. It's like a weighted average sort of thing. And we can use these, we can like maintain them. So in particular, anytime an element changes after a query, the only split points that'll change are the split point right before it and right after it. So first, we subtract the contribution of these 2 split points. Then we recalculate what the split points are here, and then we add back in the contribution of these split points. So when they change here, we can handle how our sum changes as well. And then we just print our sum at the end. Yeah, so this v part, like the amount a split point contributes, is, if it is a split point, it's 1 times its value. Otherwise, if it's not a split point, it doesn't add to the total at all, because it's the same, right? You don't need to create a new block here. Okay, so yeah, that's this v part, and then that's what we're doing here. I know I'm going through it pretty quick, but I think this idea might be helpful. Yeah, so the idea is, instead of looking at this, the high level idea is, instead of looking at it by range, we're looking at it by split point. We're saying how many times is this split point important? And then as the split points change, we can change that total easily. Okay. Yeah, I think that's useful. Cool. We're going to move on to problem D then. 2 plus doors. Yeah, this one. So in this problem, you have a bunch of edges, and you basically have a graph with some edges. But they don't describe it to you like that. They describe it as you have an array with a bunch of queries. So, you've got an array, and the queries are, if you look at these two elements and you take their OR value is some integer x. Now, the key thing about bitwise OR is that it operates on each bit independently. So that's something we should think about, right? If each bit is independent in this OR operation, maybe we can solve it for each bit separately, and then at the end we can combine all the answers. That's what we're going to try and do. And we're interested in like how do we do that? Well, let's look at one particular bit and see for this bit what is the lexigraphically smallest array that satisfies all these requirements. Lexigraphically smallest means like in the first bit, well, it says right here what they mean, so you can read this. So how do we do this? Well, we're going to consider a bit. In a bit, the only two types of things we're told are these two things, one of them is a 1, or for these two things, neither of them is a 1. When I say 1, I mean 1 or more, right? So for these two things, either they're both 1s or 1 is a 1. And for these two things, they're both 0s. Those are the two things we're told. Now, we're only considering this one bit, right? So effectively, we can think of everything as either being just a 1 or a 0. And we need to figure out, okay, can we put a 0 in the first position? If we can we put a 0 in the second position? If we can we put a 0 in the third position? Okay, we can't put a 0 in the third position. So there's a 1 in the third position. So we know the array starts with 0, 0, 1. Can we solve the rest in lexigraphically minimal order? That's what we're going to try and do. Now, if we're told these two things are both 0s, then obviously they're both forced to be 0, right? So if the OR of two things is 0, both things are forced to be 0. If the OR of two things is 1, if those things are the same, then that thing is forced to be a 1. But if they're not the same, what it means is we can choose which of them are 1. Now, it might be one of those is forced to be a 0 as well, right? So it might be thing 1 and thing 2, one of those is a 1, but thing 2 is forced to be a 0. That means element 1, it has to be a 1. Even though that would be lexigraphically bigger, we still have to make it a 1. Because if we make it a 0, we can't make the other thing a 1, because it's forced to be a 0. So we can handle that accordingly, but basically at this point we just need to make our decisions greedily, right? We just say, for the first thing, am I going to run into problems if I make this a 0? And we can see pretty easily. All we have to do is look at all of its edges. I say edges, but really this is like all the constraints. You look at all the constraints and you see, for each one of these constraints, is this thing forced to be a 0? You know if it's forced to be a 0 by you can just pre-compute that, right? For each thing, pre-compute if it's forced to be a 0. So look at all of the edges from this to something else, and you see, is this other thing forced to be a 0? And if so, then I have to be responsible for this 1. So then you're responsible for the 1. Yeah, you also want to look at things before you. So if something that you've already decided, if you already decided that was a 0, well then you have to be a 1 if you have an edge to him, right? You have to be responsible for that edge. Okay, I hope that made sense. I might be a little out of tune for this because I just kind of saw it instantly. So I don't know what people were thinking otherwise, right? When I saw this, it's like I just kind of instantly focused on the answer. But yeah, there are probably other things, other paths you could go down that lead to the wrong answer. So hopefully I did a good enough job explaining the path that I went down. I'll go through the code really quickly here. So we're going to solve it for each bit independently, and then we print all our answers at the end. That's how this works. Okay. Then for each bit, what I do is first I calculate the things that are forced to be zeros and forced to be ones. It's pretty easy here. This is just, does this number have this bit? That's all this is. So yeah, first I calculate that, and then after doing that, I just decide things in order from first to the end. And this is pretty straightforward. So if I'm forced to be a 1, then I'm a 1. If I'm forced to be a 0, I'm a 0. Otherwise, I just want to see, if I make this a 0, will I run into the issue where I've made two things along an edge a 0? So the two ways that might happen is if the other thing is forced to be 0, or if the other thing was before me and I decided it should be a 0 and I should be a 1. That's this case. So if neither of those things happen, then I can make myself a 1. Wait, okay, that's not what I did apparently. Oh, yeah. If neither of those things happen, I can make myself a 0. Otherwise, I have to make myself a 1 if one of them happened. Yeah, okay. Good. And then at the end, for all of the 1s, right, we're doing this for just one bit, but if I made something a 1, then I'll add that to the total. So that's what's happening here. Okay. All right, that's D. Hopefully that makes sense. E, long way home. This one I thought was the hardest problem of this set. So we'll talk about it briefly. The idea is you've got a graph, and you also have this special condition where you can fly between any two nodes. And you can do this at most 20 times, or most k times. Now, the graph is somewhat small. It's 10 to the 5th by 10 to the 5th. So our runtime is going to end up being n times k times log. But we have to, what we're looking for here is the minimum cost to travel from node 1 to any other node if you're allowed to fly up to k times, and you can take as many roads as you want. Okay, so how do we do this? Well, we're going to kind of imagine node splitting here, right? So we're going to have one node. I mean, we're not actually going to do this, but this is a good way of thinking about it. We can have one node for every node in the graph. But we'll copy this graph. So we'll have one copy of the graph for every number of flights we could have taken. So we can say, what does the graph look like initially? And then we'll make a copy of it. And this is the graph after taking one flight. So there are two real steps here. The first step is, within a graph, we need to be able to find the minimum distance from every node to every other node, right? So we need the minimum distance from the start to every other node. Or if we've already gotten to some node after some number of steps, we need from that step to every other node. You can do that part with multi-source Dijkstra. So the way, if you know Dijkstra's algorithm, I'm just going to assume you know Dijkstra's algorithm. If you don't, you're going to have to learn Dijkstra's algorithm. But the way that works is, let's say you have a graph here, and you want to, Dijkstra's is you are at a node and you want to know, well, so let's say this is your graph. All of these edges have weights, by the way, as well. Maybe this is what the graph looks like. You want to know, you pick some start node. This is your start node. And you want to know the minimum distance from the start node to every other node. So that's Dijkstra. Multi-source Dijkstra is you have like some node and you say like, okay, you can start here, or you can start here, or you can start here. But maybe if you start here, your penalty is like 3, right? So this is distance 3, you start here. So the way you can do this is you can create a meta start node. You can imagine creating a meta start node, and then you can add edges like this. If this penalty is 0, this penalty is 0, this penalty is 3. So it's basically just the same as Dijkstra. So you can do multi-source Dijkstra's algorithm, and that will get you the distance from one node to everything else. Okay, but how do you handle the flights? The flights are the hard part. Well, after you do Dijkstra's, then you need to consider taking a flight. So here you can take a flight from any node to any other node. And then after we do that, we'll do Dijkstra's again. So the hard part that I haven't explained yet is like, how do you do this flight thing? The flight is hard. That's like a completely separate problem. But the Dijkstra's is easy enough, right? It's a common algorithm. You can learn it. It's pretty easy. It's a very common graph algorithm. So the question is, how do you do this flight thing? Well, the flights are kind of tricky because you have n squared edges, so you can't even consider all of them. You have to find a smarter way of doing it. And the observation here is the following. I kind of wrote down the math, so I'll show you that. What we're going to want to do is considering flying to every space. And we're going to say, if we fly to this space, what is the place we should fly from, right? And you can do this using something called convex hull optimization. Basically, what it is at a high level is you have like a bunch of lines here, and you kind of like take the convex hull of these lines, or the convex envelope maybe. So we want, we'll take like this, right? So you can imagine if you have a bunch of lines, you find the max, and then you can query at some x what is the max. And you can do this fast, right? If you do it in a certain order, you can do it in order one time. So yeah, we're gonna do things in one order. We're gonna add the lines in one order. We're gonna query in an order, and then we get everything very quick. So yeah, this is convex hull optimization. It's a somewhat advanced trick, but once you know it, you can just plug it in here. And the idea is, you have a bunch of lines. You want to see what's the max at some position, or what's the min at some x coordinate. And you can do the math. Like, here's what the math looks like. So you want to find them. So let's say every element has a start cost ci, right? And this is the cost to get to it with roads. And then you're going to take that ci, and then you're going to fly to position j. So you say, for position j, what is the best I could fly from? And the cost you have to pay is the cost to drive to the other one and then fly to u. Now, if you do the math, it turns out this is the same as this. So if you factor this out, you get I squared minus 2ij plus j squared. That's what this is equal to. Now, you know you're flying to position j, right? So this j squared thing, this is going to be here no matter what the I is. So you can take this out of the min part, right? You can just calculate this part separately. And then this part is more or less a constant. So if you're flying from a particular thing, this part isn't changing. So you can make this part like a constant. And now we have a form of a line. We have a line, we want to find the lowest line where you have mx plus b. The m part is minus 2i, the x is just j, and then the b is this. So we want to find the minimum thing here. We'll query the minimum one. And that's where convex hull comes from. So we're going to, the idea here at a high level is we build our graph, we run Dijkstra's. This will be drive everywhere. Then we do convex hull. This will say for everywhere, try and fly here from the best other place. And we can do this in n log n. And then we try and drive everywhere. So because you might drive, fly, drive, fly, drive, fly, and so on. Okay. Yeah, that's what's going on here. The Dijkstra's is very simple. It's just classic Dijkstra's. So yeah, you can stop and read this code if you'd like, but this is just, if you know Dijkstra's algorithm, you know how to do this. This convex hull part is kind of tricky. Yeah, I'll show you the E2 because it's just better. Yeah. So here's the convex hull logic. It's actually pretty simple. I mean, it's actually just what I described, but all the magic is hidden in this hack pack. So this is a lot of stuff. I'll go through here slowly, I guess, and then pause it, and you can copy it if you'd like. But yeah, this is written by my ICPC teammate Josh Fair, great guy. We worked very well together, and I'm glad he was able to write it. I've written tests for it to verify that it works. So yeah, it's kind of legit. Okay. Cool. Yeah, that's the solution to this. Hopefully that made sense. If you don't have convex hull, it's very hard to figure out on your own, but I guess it is possible. Okay, last one is problem F. This is a very easy problem, actually, so I'll just talk about how you do it briefly. The idea is, well, the problem is you have a 1x1 square hidden somewhere in a 100 by 100 field, and the square is axis aligned, so it's something like this. And what you can do is draw a polygon, any polygon you want, and the judge will tell you the area of intersection between your polygon and the unit square, the axis-aligned unit square. The axis-aligned unit square might not be at whole number coordinates, right? It can be at, like in this case, it's at 0.5, 1.5, right, or 1.5, 0.5. So it's not necessarily on a unit, on a particular unit, but yeah, it's somewhere there, and it is axis-aligned. And then you want to be able to guess what is this corner. Now, yeah, I guess I'll just tell the solution, right? You have up to 5 queries. You only need 2 of them. Maybe you only need 1. Probably not. Maybe with a complex enough thing, you only need 1, but I use 2. It's pretty easy to do with 2. Here's the idea. So you've got, here's your thing. You've got a unit square somewhere. Looks like this. We're gonna build a polygon that looks like this. So it's gonna go like this, and then it can just go like, let me try and get this right here. Yeah. So it'll be something like this. Yeah, and you get the idea. And then we'll keep going. We'll keep making these. I guess we'll just finish it. So we make this like this set of like spikes basically. And what the spikes can tell us. Yeah, perfect. Okay. And then there you go. So our polygon is like this sawtooth kind of thing, right? It looks like this. And the area of intersection is this part here, right? So this area of intersection is proportional to where the center of the box is. If the center of the box is here, the area of intersection will be about 100, right? And if it's here, it'll be 0. Obviously, it can't ever be there because then half of it would be negative, right? It's probably negative. But like if it's here, it's, yeah, it's whatever. It's like the average y that's in here is equal to the height at the middle. So we can consider that like we're told the thickness of this part here, right? This is basically what our queries tell us. They tell us like how thick does this intersect? And we don't have to worry about the square being offset, right? If the square is offset by a certain amount, sure, we'll lose some of this spike, but we'll gain the same part of this spike because the height between these spikes is equal to the length of the square. So it doesn't matter what the square y is here, right? No matter what the square y is, the x will be the same, right? We're just interested in like the x part. And the x part will give us the height at the middle of the square. Because this is a triangle here, right? This is some triangle, it looks like this. So you can imagine cutting this part over and flipping it upside down. And then you get a square, or you get a rectangle here like this. So that's effectively what we get. So yeah, we can get the x coordinate with one query, and you just rotate everything, you get the y coordinate with one query. It's actually really easy. The only hard part is formatting your output, but I'll explain that in just a minute. So this code just prints the sawtooth in a 100 by 100 pattern. So I just ignore I mostly ignore the width and the height. I'm pretty sure you can just ignore them entirely. Yeah, I'm pretty sure this should be correct, but I don't really know. Because I don't know why I was wrong on the first time, but yeah. And then I print my answer to 8 decimal places, always. So yeah, that's it. That's the solution. It's pretty easy. I had like some weird issues with like if you just print these as a double, apparently it's wrong. I don't know, like it's possible I'm printing too many digits. It's possible that it's doing one of those like scientific format things and that breaks it. But printing it like this is good. In general, this is a good way of printing floating point numbers, especially for geometry problems, because it'll round it after 8 digits for you, and it's just very nice. So yeah, that's solution to problem F. It's a pretty easy problem, I think, overall. Maybe, I know I'm just like kind of biased towards geometry problems, but I think this is a pretty easy one. So, yeah, there you go. All right, well, thank you for watching. Have a great day, and good luck upsolving. Right? Hopefully you pass this some tests. All right, goodbye.